So I'm going to take a few seconds to revisit what happens with atoms. There are approximately 92 elements in the periodic chart, so they're not all available. But you've got sort of this is sort of a palette of atoms to work with. They're distinguished, of course, by the number of fundamental charges on their nuclei, which then attract an equal number of electrons. So each of the atoms, I don't know, sodium, mercury, helium, they're distinguished by the number of atoms they have, the number of electrons they actually have as attracted by their nuclei. That gives them an idiosyncratic behavior that's sort of unique to that element. You can identify the elements by their electronic structure, and their electronic structure is most visible in the light that they emit when you add energy to them. And why is that? If you have the atoms, pick one atom. Let's pick sodium just because it's, okay, pick sodium. If you make a vapor of sodium, so just the individual atoms all by themselves, and you make it a low density vapor, so the atoms are not only by themselves, but they don't really interact with anything. They're kind of in empty space, rattling around. And you add energy to them in almost any way which you manage to get enough energy in them that they pay attention. Very small doses of energy will not cause anything to happen to them, but enough energy, the energy is, say, associated with a hot flame, will typically rearrange the electrons in their orbitals. Right? The electrons at room temperature, they tend to settle into the lowest energy orbitals that are possible. They just don't have excess energy around with which to work, so the electrons are all down there in what's called the ground state, the lowest possible arrangement of standing waves. If you throw in extra energy, whether it's by an electric discharge, where there are charged particles whizzing back and forth, or whether it's in the flame of a firework, or just a Bunsen burner. You probably have seen this in chemistry class. If you just throw sodium into a Bunsen burner, you get yellow light out. Why yellow? Well, it's because when you put in this extra energy into sodium, the simplest thing that can happen is a rearrangement of an electron. Basically, one electron really does all the movement. It shifts from where it is in the ground state to the first excited state. That is the next standing wave up there, normally empty, in which the electron can live. So it goes to that next available state, and it stays there briefly. The standing wave by itself was sort of stable, except that it tends to decay by emitting light and then plop back into the ground state. And when it does that, the energy difference between the excited state and the ground state is just enough to build a yellow photon. Remember, there's a relationship between energy and the frequency of the light. They're proportional to one another, and out comes the yellow photon. So at low pressure, sodium loves to emit these yellow photons because that's based on the structure of the orbitals that are unique to sodium. If you go to a different, let's see, it's the only one it's one I know well. Neon, you've seen neon, when it's rearranged, its simplest rearrangement involves also emitting a photon, typically in the red. So they're all unique to them. The problems that talks about strontium, that first step between the sort of the ground state, and when you put energy in, you get an excited state that has just the right amount of energy when the electron leaves and goes back to its ground state orbital. It emits a red photon, barium a green photon, and so on. So that's the world of the low pressure. The low pressure discharges show you atomic structure pretty straightforward, just right there in your face. You see the light that's coming out is an indication of the spacing between orbitals. Any questions about this idea? How you put the energy in doesn't really matter as long as there's enough energy around. So collisions in a gas discharge do it, and the fireworks do it. This is the colors of fireworks. If you have higher pressure, things are more complicated because there's a good likelihood that the particles are getting hit all the time, the atoms are getting hit all the time. And there's a very good chance that after receiving energy and going into the first excited state, for example, that rather than having the time it needs to emit a photon and go back down to the ground state, it may get hit again. And it may get knocked into a yet higher excited state, and so on, up until you've let it explore arrangements that are unlikely at low pressure. And therefore, you get radiative transitions. That is the process of moving from orbital to orbital, in which the electron moves from this orbital, which it normally wouldn't be in, at low pressure ever, to this orbital, which it also might not be in at low pressure ever. And that emits, I don't know, maybe that's a blue photon. So you get new spectral lines coming out of the discharge at high pressure, or whatever the context is, however the energy went in. If it's at high pressure, you don't count on it emitting its favorite frequencies that associated with low pressure. Is that okay? That was the main story I wanted to make sure that I try once again to pass along. So when you see fireworks, you are seeing specific atoms up there glowing, and they're pretty easy to identify. If it's red, it's probably strontium. If it's green, it could easily be barium. Copper is sort of in the blue-green too. A bunch of other atoms around there. Okay. Story that I'm trying to build here now, still, as we'll see, it's still related. The light that comes out of an LED, it's still a radiative transition. I can tell you that in advance. It's still a case where an electron is going from one standing wave to another, in which the new standing wave it arrives in has less energy. So the electron is giving up energy to shift from one arrangement of wave crests and all that to another arrangement of wave crests. And it doesn't need the energy anymore. That energy comes out, well, as light. Okay, so where I approximately left off, or where I was just showing you just at the end, this idea that if you make a semiconductor, semiconductors are technically, they're insulating, that is, they're insulating in the absence of light and heat. If you let everything be very calm and settled, they have a full valence band and an empty conduction band. So all the electrons are packed in. I guess I can go back to the previous slide. Here, where are they? There. All the electrons are boxed in that valence band. They can't move in response to an electric field. The Pauli exclusion principle plays a key role here by simply preventing any bunching up of electrons in the same standing wave. So they're all sitting there staking out their current standing wave, and they can't do anything else about it. And the conduction band being empty doesn't help. And it's separated by enough energy that without light, without heat, the electrons will never get enough energy to move into a conduction level standing wave. So they're just stuck. Any question about that idea? This is the basis for insulators. General insulators like this. In a semiconductor, it's an insulator, except that the energy needed to move from a valence level to a conduction level isn't all that great. And so it can happen in the presence of light or heat. So in a really good insulator, salt, for example, is actually quite a good insulator. The energy needed to move one of these electrons from a valence level to a conduction level is huge. It's associated with an ultraviolet photon. It's not super, super huge, but that's pretty huge. It doesn't happen very easily. In a semiconductor like silicon, it moves pretty easily. In fact, any visible light photon carries enough energy to move an electron from here to there. So that's ordinary silicon. What I had up here is doped silicon. So it's silicon in which they've deliberately put in impurities into the crystal that either add extra electrons into the mix or remove electrons from the mix. And the p-type semiconductor is the one that's missing electrons by virtue of having added to it elements that don't have quite as many electrons as the actual semiconductor does, the normal, like silicon. So it ends up with some empty, unfilled levels in the valence band. The n-type semiconductor is the one that's got extra electrons. They got to go somewhere, so they go into the conduction levels. So there they are up there sitting around. And both of these can conduct electricity because if you apply an electric field to them, the electrons can move. They're empty spots to work with. And electron can hop from its current level to some nearby empty level that's very close in energy and therefore doesn't require any big effort to move. All right? Questions about n-type, p-type semiconductors? The idea of doping. It's just, okay. when you touch those two materials together, this is where sort of I really was leaving off. These electrons up here in the N-type semiconductor's conduction band have more energy than any of the other electrons around, and in fact they have more energy than they would have if they were able to get into the valence band of the nearby but not quite accessible p-type material. So when you touch them, some of those conduction level electrons, conduction band electrons, migrate across the physical junction between the two different kinds of material, the N-type on the left, right, p-type on the left. They migrate across that junction and are able to go into empty valence levels. It's okay? Questions here? Anybody? Hopeless. All right. That process of migrating across creates a separation of charge here in this central region, around this PN junction, it's called. There are electrons missing from over on this side, and therefore this acquires a negative net charge. That is not true. This is positive net charge. This has a negative net charge. I got to fix this drawing. Oops. So this actually has, cross that out. That's negative net charge because electrons came here. This has positive net charge because electrons left. Is that okay? So there are two consequences. There is an electric field in here that points from the positive side to the negative. This electric field points to the left. I haven't drawn it in there. And it makes it difficult for any further electrons to come in there. They're pushed backwards against if they try to come in here, they're pushed backwards, because electrons, after all, are pushed opposite electric fields. I mean, I realize this is a lot of words and it's hard to visualize, but the migration comes to a stop because basically each new electron that tries to make the crossing it gets less benefit out of it until eventually it gets no benefit out of it. It's pushed backwards so ferociously that it doesn't bother. So you end up with a limited flow of charge from the N-type side to the P-type side, after which the central region, what's called the depletion region, it has no longer any empty spaces, any empty levels in the valence band. It's filled. And no electrons in the conduction band. It's empty. Electricity can't flow through this region. Won't carry current. It's an insulator. It's back to being a good insulator. Well, good enough. All right? So this seems like a strange structure. It has a natural separation of charge in it all day, every day, and it doesn't carry electricity. Where this becomes interesting is when you deliberately try to push charge one way or the other through this whole structure. If you try to push charge in what's called the forward direction, the direction actually which charge will flow, and charge, instead of talking about charge, this is the awkwardness of charge being a positive concept and electrons having a negative charge. I'm going to stop worrying about charge. Let's watch the electrons move. If you try to push electrons through this, from the right side to the left side, from the N-type material to the P-type material, and you can do the pushing with electric fields, it's not a big deal. You start shoving them in, and where do they go? Well, they can't go into the valence band because it's full. It refuses to take any more electrons. They cannot have those those standing waves. So they instead go into the conduction levels process, which means they have to be given an extra dose of energy to do this. And that energy is going to come out of the electrical, whatever's pushing the current, pushing the charge or the electrons through the system is going to pay for this. You need a battery to do this. You shove them in here where they come in with extra energy, and they will actually be able to migrate through the empty levels that are present in the conduction band. They can do that, no problem. They go rolling in there because it's all full empties, and they will, if you push hard enough, they'll actually make it past the electric field that's in here that normally had stopped the migration of electrons. You can overcome that backward push and get them to cross anyway. So they go across, and the electrons are now in the P-type material's conduction band. which is normally quite empty. In fact, it's so empty that even the valence band has empty spots. And one of the electrons, having crossed the junction, they can undergo some sort of energetic transition. They give up energy to go from the higher energy conduction band to the lower energy valence band. Again, they don't have to move anywhere. They don't have to move to the right or the left. They just have to go from higher energy wave to a lower energy wave. And that's what they do. They go from a higher energy level to a lower energy level. And then they can move through the empty levels that are present in the p-type. Why are there empty levels there? Moments ago, there weren't any empty levels in the central region. Well, that's because if you begin to suck electrons out of the left side, you shove them in on the right side, you suck them out of the left side, you create empty spots. You coax, the electric field has coaxed electrons out of this area and made empty places for electrons to go into. So this is a forward biased, why the word biased, I'm not quite sure, forward biased diode. If you push electrons in from the n-type side and suck them out on the p-type side, and you do this aggressively enough, because you have to overcome this electric field in the middle. If you do it aggressively enough, current can flow through the diode. I mean, if you take away only one tidbit out of this, it's that if you take this junction, this PN junction, which is created by touching those two semiconductors, and you push charge in the correct direction, you push electrons in from the correct side, the N side it happens to be, and take them out the P side, you can get them to move all the way through the whole device. When this is going on, the depletion region is gone. You've actually shrunk it. The electric field compresses the depletion region, that insulating region with no electrons in the conduction band, no valence, no empties in the valence. It compresses that to zero. It just disappears. And current flows. Happy, happy. If you try to push charge electrons the other way, so if you try to shove the electrons in from the p-type side and suck them out of the n-type side, you make the depletion region bigger. It's not helpful. So here we're shoving electrons into the p-type semiconductor. What do? They go and they fill in yet more of the last remaining empty levels in the p-type valence band. That isn't helpful. And if you suck electrons out of the n-type side, you clean out the conduction levels until they're all empty. That's not helpful either. You create a gigantic depletion region where all the valence band levels are full and all the conduction band levels are empty. Questions about this? Really? I haven't talked about light really yet, but this is sort of the simplest electronic device where it's really working with electrons. That's where the word electronic as opposed to electrical. I think the distinction is that you're really paying attention to the electrons and what they're doing. And this is a device that is a one-way device. It's a one-way device for electrons. They can go through it in these pictures from right to left, but they can't go through it from left to right. And diodes show up in all sorts of electronics. There are lots of them already in this room in all these gadgets. There are more sophisticated devices that we'll talk about, one in particular that'll come down in the future. But if you understand how this works, the other ones are pretty straightforward. So it's really manipulating, working with the electrons in a sophisticated way. In a conventional diodes are used for example, to take alternating current and create direct current out of it. Alternating current, you've got two wires, and the voltage of one is fluctuating from being higher than the other to lower, higher, lower. And the current flows first one way through your desk lamp maybe, and then the other way through your desk lamp. The current's going back and forth. How do you deal with this? Well, if you send the current into the right collection of these diodes arranged properly, you can use their one-way character to make sure that they're always flowing a certain direction through some wire farther on down the system. You can imagine doing this with one-way streets. If you want to make sure, starting with cars heading every which way on one road, collection of roadways, if you want to make sure that they always are fed onto a highway, heading the correct direction on this lane, you use one-way streets to do that. You can make sure that nobody goes backwards onto that highway. Or that whenever they are heading towards the highway, they get funneled by one-way streets onto the correct lane. They're not going on the left side of the road, going. I'll stop. Okay, so diodes show up in all your power packs for your AC adapters when you plug those in. One of the ways in which the alternating character of electric current in our power grid is unalternated, is turned into direct current, is with diodes. All right, rather than dwell on that any further, I will point out that LEDs differ from ordinary diodes really in a sort of one characteristic. When these electrons over here in the conduction band make the transition to the valence band, giving up energy, in conventional diodes, that energy is released as heat. The diode gets hot. In a light-emitting diode, a substantial fraction of these electrons, when they make that transition, they do it radiatively. They emit light. Simple as that. That is, it's easy to say. To actually engineer the materials to do this, not so easy. It's been a long process. The past 30, 50 years have been involved in trying to perfect the building of these structures to be as efficient as possible, to emit light as often as possible when those transitions occur. The light that's produced is related to the energy gap between, the band gap between the conduction band and the valence band. Because when the electron shifts from the higher conduction band level, higher energy, to lower energy valence level, there's a specific energy that has to be released. And associated with specific energy is a specific frequency and therefore color of light. So when you make a red photon, which is a low energy photon, it's on the red end of the spectrum, it has low frequency and therefore low energy, it's easier to make a red photon. And the light-emitting diodes in the red showed up first. And they involve a small band gap. The energy to make that transition is relatively dinky. Green takes a bigger, it's a more energetic photon. It needs a bigger band gap to have the step release a green photon's worth of energy. And finally, blue LEDs are within your lifetime, I guess, that they become common and useful. And because of how we see light, red, green, blue being the primary colors of light, to build proper color displays, for example, the jumbotrons and stuff, they needed red, green, blue LEDs to do this. And so prior to the development of good blue LEDs, there were none of those jumbotron things. So displays were limited in color. They worked with green and red, no blue. So with green and red, you can make people see yellow by overlapping green and red in space. That tricks your eye into seeing yellow. So the displays were all limited color, red, green, and yellows. Once they had blue LEDs under control, now you got the whole spectrum to work with. And so things like jumbotrons became possible. It's okay? What else? Maybe good. Let me just look and see whether I have anything else I wanted to tell you about. Okay. Any other questions about LEDs? I should show you rather than just barrel ahead. Stop that. I tell you one exception though. The colored LEDs. So let me do it. Remind me to tell you about white LEDs. Okay, so here, fun and games with LEDs. These are 4 different colors. They involve 4 different materials in there. They are diodes, They're one-way devices for electric current. I'll show you that in a second. But they have different band gaps. They're engineered, the chemistry is different. So the band gap isn't something you can just sort of dial with a knob. You have to change the chemistry of the PN junction. And so this is the lowest, the smallest band gap gives you a red light. Next up, you get sort of this yellow. The green is a bigger band gap, and here's the blue I talked about. This is a large band gap diode. Okay? I have them wired in series, meaning the current enters at one end, goes sequentially through blue, then the green, then yellow and red, and then goes back to the batteries. So I'm using two 9-volt batteries to make it operate. Okay. Same idea, just to show you this, and then I got a tidbit to tell along with it. Talking camera. There. Are we looking down at it? Yes. Okay. The details around here don't matter so much, except for the voltage. And I love it when static electricity makes this guy move. Don't do that. Here is the light-emitting diode. And let me first show you, it's a diode. If I turn it on, so that now it's working. If I reverse it and try to send current through it backwards, nothing. It truly is one way. Okay? So this, now I'm doing it the right way now. I am sending electrons in the N-type side, sucking them out the P-type side, and there is a voltage drop across this device. We have to do it in reverse, because then we have to think about charge. But the details of there don't matter again, but there is a voltage difference between entry and exit of 2 volts right now. Why do I know it's 2? There it is, 2. Okay? 2 volts between entry and exit. That means that every electron that is going through this device is giving up energy associated with a 2-volt change. It's going from 2-volt change in the environment. That means it gives up the energy associated with a 2-volt change for 1 electron is called 2 electron volts. The electron volt is actually a unit of energy. It's a very dinky but quite useful unit of energy. It's the energy that one fundamental charge needs to go from 0 volts to 1 volt. If you want to push, the work of pushing that fundamental charge, taking it off the 0 volt wire and shoving it onto the 1 volt wire where it's repelled, it doesn't like to go there. It takes a little dose of energy, it's 1 electron volt. So right here we're seeing charges enter and leave having given up 2 electron volts. I'll sweep everything else under the rug and not worry about it. But the fact that there's a 2-volt difference from there to there, each charge is releasing 2 electron volts of energy. Are you okay, or questions about that idea? Details, and will you remember what an electron volt is? Probably not, but it's a small dose, and we've got it under control, and the voltage is giving us an indication of it. Well, red photons carry with them about 2 electron volts of energy. There it is. It takes about 2 electron volts to build a red photon. If we try to send current through this diode and we don't push hard enough, for example, if we go down to 1.5 volts, the diode doesn't carry any current at all. We build no photons. So to build a red photon, we got to push hard enough to pay for each photon, basically. You can think of it as that way, and it's about 2 volts of voltage drop we need to make that payment. All right? If we go to the higher band gap semiconductors and light-emitting diodes, that was the red LED. If we go to the yellow, do I have a yellow over there? Maybe. Certainly green and I think a blue. We need to pay more. So if I put in place of the red LED, come out of there, this is probably yellow or orange. Let's try it. There, it's yellow. Okay? This one's a little more picky. We got to go a little higher in energy, not very much, but a little bit. It's not very compelling proof. Let me go for green. We ought to have to push. Yeah, it's just dim. To get it to really go, I got to go push a little harder. Actually, I see it. Okay. I think I got to look more carefully. Let's see the red. we're at 2 exactly. Is that clear? Yeah, 2 exactly. If we make a yellow photon, we're a little above the 2. You can barely tell. It's not very convincing. By the time we get to blue, it'll be convincing. We're a little higher still. Nah, barely. Not the world's best demo. Okay. Blue, uh-oh. Building a blue photon takes a lot more push. There we go. To get to blue, we got to go up to over 3. I should have just stuck with red and blue. Forget the other ones. They just like, secretly not great. You need to push, you need to create a voltage drop of over 3 volts to get the blue to go. And this is one of the reasons why you have to put a certain number of batteries in all your LED-based gadgets. For example, what? LED flashlights and stuff. Some of them are colored flashlights. You can operate a red LED flashlight with 3 volts, which is two AA batteries will do that. To operate a blue flashlight, you need a 3rd battery, a 3rd AA battery. You need more voltage. Typically, you're using lithium cells, which provide voltage rises of 3+ volts. So you can operate one of these off of a single lithium cell. But anyway, that's a little story here. Anything else I want to tell you this? Oh, white LEDs. So I do want to make sure you understand that you got to change the chemistry of the junction to get the different colors. You're changing the band gap, and therefore the energy that the photons carry away with them. Is this okay? All right. White LEDs. They're not, how do you make white? Well, we see white whenever our red sensors, green sensors, and blue sensors are all simultaneously sensing light at about equal intensities. And so I guess the most conventional way of making a white LED is to start with the blue LED. Blue light, okay, you let some of the blue light through, because that's going to be the blue component of the spectrum to make us see white. But you need to get red and green from somewhere. How do you do that? Use a fluorescent material. Use something like what's up in these lights, the phosphors up there, to take in blue photons, throw away some of the energy, and emit some red photons and some green photons. So that's what they do. It's a white LED, such as I carry around with me. This is actually a blue LED with a phosphor coating that creates the missing red and green. And they get it about right to get so that the overall intensity pattern of the red, green, and blue is about right for us to see white. It's not a thermal spectrum. If I had a gadget to show you the spectrum, it's all messed up. It's not real white light. They're doing their best, but it makes us see white. It looks pretty good. There are more sophisticated ways of making white light, the most sophisticated being to actually combine in a single package a red LED, a blue LED, and a green LED, and to turn them on, run current through them at about the same intensity. So you're basically doing this without that guy in the middle, without the yellow one. You're doing this in a carefully engineered way so that you get just the right balance of colors. All right? So yeah, I should probably take apart some LED light bulbs and see how they're doing it. They're probably doing it with, you cut it open, you probably find multiple LEDs of the different colors. I suspect that's how they actually create the white for a serious illumination light bulb, rather than using the phosphor. All right? Anything else about LEDs? All right, let me do lasers and then not go on too much. So how does laser light, have I got that up there? No, I don't. Try again. There we go. How does laser light differ from regular light? And the answer is that it's a much more sophisticated light. It's a single wave, or a very limited number of waves. In an ideal case, the laser light is a single wave. It's essentially a copy of a single initial photon, copied many, 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 many times. As a result, the entire wave can interfere with itself. If you break it into two halves and let it overlap it, the whole thing interferes with the part A and part B totally interfere. Dramatic interference effects. What else about it? If you try to focus light from a conventional light source to a small spot with some sort of lens system, it's kind of hit or miss. You can make a modestly small spot, but not terribly small, because the light from a conventional light source is composed of countless individual light waves, each with its own characteristics, subtly different from the others. It might be different color, it might be different in exactly which way it's heading, and so on. And so to organize this herd of stray cats, you just can't get them all into a single tiny spot. That's not true of the light from a laser. Light from a laser is one beautiful organized wave, and if you manage to focus one photon where you want it, all of them are focused where you want it. They all go together. They're all one big thing. It's what's known as coherent light then. So incoherent light is sort of the shotgun version of light. It's just every photon for itself. Coherent light is one giant wave. The whole wave works together. It's not the first time we have seen coherent electromagnetic waves. The radio wave coming out of an AM radio station is a coherent wave too. It actually, believe it or not, is composed of photons. The act of transmitting creates a whole lot of them. The frequency is very small, after all, coming out of a radio wave. Much smaller light, anyway. And so the energy in a radio wave photon is tiny, almost unmeasurably small. But it is still emitted and absorbed in photons if you look down in enough detail. And the emission process, though, from a radio antenna creates a coherent wave. All the photons are the same. And so it is coherent electromagnetic waves. They're not as interesting as as light coherent waves. And those can't be produced by running charge up and down in an antenna. We don't know how to do that fast enough. So we have to use a different technique to build coherent light. Coherent radio waves, easy. Coherent light, hard. And the way it's done is with a duplication process. So you use a material that has energy already added to it. So it's essentially in excited states. For example, atoms that have been put in excited states can do this duplication process. If you put atoms or something like an atom into an excited state, so you've got its electrons sitting there in standing waves that have extra energy, those electrons can either emit light themselves all by themselves, which they would naturally do if you wait long enough, in which case they will produce incoherent light. For example, sodium atoms all piled up in the first excited state will individually produce yellow light, just photons, and they'll all be independent of each other, and it will be incoherent light. But if you send along light that these atoms are capable of emitting, there is a statistical advantage to them to duplicate the light. So instead of emitting the light in any old which way, when a photon of light comes along and passes a sodium atom in the excited state, and that particle of light is the right one, it's one of those perfect yellows that sodium loves to emit, there's a good probability that the sodium atom will emit the same light. And what came in as one photon will go out as two photons that are identical, and therefore a big wave. And if you have thousands of sodium atoms all in the same excited state, you could duplicate that initial photon thousands of times, millions of times, 10 to the 20th times. And that's the concept of a laser. Laser is an acronym for light amplification by stimulated emission of radiation. The stimulated idea is don't wait around for these atoms to emit light themselves spontaneously. Stimulate the emission of light. Send along light that they're capable of emitting, and they're for things having to do with quantum mechanics and the mathematics of quantum mechanics, it can be shown that there is a tendency to duplicate the light. And actually, the more intense the light has become, that is, the more copies are already present before they pass one of these atoms that's capable of duplicating it, the more likely it is to duplicate it. So it's a runaway process. And that's the basis for all the lasers you've ever encountered. They are taking at least one initial photon, and they are just duplicating the bejeebers out of it. So here's the idea of incoherent radiation. This is just my cartoon. You can have excited state atoms doing radiative transitions, everyone for themselves, or you can send along an initial photon and have all the other ones duplicated. And that's the stimulated emission. And it creates coherent radiation. What I want to show you, though, before finishing here, that the idea of amplifying light is the basis for a laser. You start out with dim light, as my drawing here, and you send it through a material that is primed with energy and is capable of emitting that incoming dim light, and it will duplicate it. Now it comes brighter light. So the laser starts with just a pure amplifier. That by itself is an optical amplifier. The point being, we haven't said where the dim light comes from. If you take an optical amplifier and you send its output light into its input, you get feedback, right? You've seen this, this is the experience you've had, usually unpleasant experience, when somebody takes a microphone and makes it so that the microphone hears the amplified sound from the microphone. I could do it easily, I won't do it. You know what happened? I turn up the microphone here, we're going to get squeals, right? That's feedback, where the microphone hears the speakers and amplifies that, which makes the speakers produce more of it, which amplifies. It's a catastrophic runaway process. You okay with that idea? You can do the same thing with lasers. You take that amplifying medium and you put it between mirrors, so that essentially the output goes back in the input. And yeah, it goes back left and right in this case. But it amplifies, the light that goes through gets amplified over and over and keeps going back and forth. And so most lasers you encounter, they start with one photon that just by chance happened to go through the laser medium and bounce off a mirror and go back through the laser medium. And it gets amplified and going back through the laser medium, and bounces off another mirror. It goes back through the laser medium, gets amplified over and over and over. And that's this laser here. This is an old helium neon laser, and to get this is aux east. You should be looking at this. Did I do? No. Camera on tripod. Not right. Try again. Camera. Try again, West. Too many operator error. Oh, there we go. I can't stand seeing myself twice. Okay, sorry. Fine. All right. If I turn this guy on, it's a gas discharge. So there's high voltage that's run through. It starts here, goes around, goes through a tube at the bottom. It's a gas charge in a mixture of helium and neon, which are this is the original laser, actually. The discharge creates excited helium atoms, which then bump into and transfer energy to neon atoms. So it's a little bit subtle how it does this, but it manages to put lots of neon atoms in an excited state. And neon, as you know, loves to emit red light. This manages to get what's called a population inversion, where the neon atoms in the excited state are dense enough that they can, they're prepared to emit red light, and there are not many atoms that emit red light and going from the excited state to a lower state. A lower state that is rare, that is, there are not many atoms in that lower state. The point being that it can emit red light, but it doesn't absorb the red light very much because there are not many electrons sitting there waiting at the bottom of the optical transition, the radiative transition, to go the other way. Let me just leave that detail. The point that's important here is there's a technique used to get the neon atoms all ready to duplicate a particular photon. They also spontaneously emit that same kind of light just by chance, and once in a while, one of those photons will, by chance, bounce off the mirror at the end, over here, and go back through the medium, and then bounce off the mirror at this end and go back through the medium, back and forth and back and forth. And that process allows that original photon to be duplicated over and over and over. And if these were both perfect mirrors, that process of having light bounce back and forth and become a giant wave would be present, but it would be boring because no light would come out. So instead, they don't coat those mirrors perfectly. Those mirrors are sophisticated. They're actually an oil film, they use interference to be mirrors. They're mirrors the way a soap film is, or the way diachronic glass that I had in one of the problem sets. This one is also a little leaky. Can you see that there's a little light coming out there? So there's actually a very strong wave going back and forth inside the bottle here between the two mirrors. And the mirrors are not perfect. This one is almost perfect. A little comes out. This one is considerably less perfect, and a lot comes out. Is that okay? This is the basis for all these laser pointers and stuff. So, and much more sophisticated lasers. There are lasers, yeah. I could go on. There are some very sophisticated lasers in this building. So here too, I should really make myself happier. This is a red diode laser. So this is the same. It's a diode very much like a red LED. It's got the band gap that gives you that red light. The whole works just like that. The difference is that instead of using the spontaneously emitted light that comes from an electron dropping from the conduction level to a valence level, it's being stimulated by the passage of red light, and it duplicates the red light. So this is essentially a high-tech LED between two mirrors, and you get amplification this way, and so you get a spot. And the fact that it's a single photon duplicated in many ways means that you can do great, amazing optical things with it. Like it stays as a very narrow beam for a very long distance. You can't do this with a flashlight where all the photons are different. This is one identical photon, many copies, and it's got terrific characters. What I can go to at the end here, let me blank that guy. I got a laser up here just to show you the interference effects you get with that. Where's on? There's on. What you're seeing up there on the screen, the middle of the main screen, this is a green laser that would be a single spot, except it's being sent through two little narrow slits. And those narrow slits break the wave into two partial waves, which then go forward. They travel as outgoing ripples, and they manage to overlap and give you constructive interference at the center and destructive interference nearby. I'm going to go over to this guy. If I go through multiple, I'm sending it through multiple slits. This is now going through several slits. You get constructive interference where the spot is bright, and everywhere else you get destructive interference. The fact that you can get that kind of contrast, and I've waxed poetic about this in the past, that you get such amazing contrast, you can't do that with ordinary light from a flashlight. You get this only when you're working with these super coherent giant waves. And